So how to classify the chemical reactions? Based on how many phases involved in these chemical reactions, we can simply classify them as homogeneous reaction or heterogeneous reaction. Homo actually means this chemical reactions happens in one phase alone or only in. And heterogeneous chemical reaction means this chemical reactions happens in the presence of two or more phases involved. So if we don't add any catalyst inside these chemical reactions, then for homogeneous reactions, for example, like most gas phase reactions or most liquid phase reactions, burning of them belongs to homogeneous reaction. And regarding to heterogeneous reactions, for example, like the burning of coal will be involve the gas oxygen react with solid coal, or attack of solid by acid that will be involve the liquid acid and the solid. And also some gas liquid adsorption reactions only it belongs to heterogeneous chemical reactions. But why we need to highlight these reactions belongs to homo or heterogeneous reaction? Because if every reactants in the same phase, you don't need to consider the transport of reactants. But for heterogeneous reaction, you need to consider the transport of reactants, right? For example, like if we consider the burning of coal, that means you have the gas oxygen react with a solid coal, right? So you need to consider when you want to evaluate or estimate the reaction rate for this burning of coal, this heterogeneous chemical reaction, you cannot just simply consider the chemical reaction rate. You still need to additional consider the transport time of the oxygen to arrive the surface of coal, this solid coal. So it will be something you can consider as a series reaction, have a transport plus the reaction. So this is why we need to highlight the heterogeneous reaction. For each heterogeneous reaction, when we talk about the reaction rate, you instead of, you need to consider the transport time between two phases, and also plus the reaction time. Okay, and the other thing is some chemical reactions you did added some catalyst to reduce the energy barrier to speed up the reaction rate. So it can also be performed in homogeneous reactions or heterogeneous reactions. So let's focus on the catalyst reactions. So in this case, we call it as a catalytic chemical reactions or catalysis. So catalysis is the increase in the rate of chemical reactions by what? By ending the catalyst. But remember, the catalyst is not consumed during these reactions, and it can be continued repeatedly. So if we still use the chemical reactions we talked in previous slides, A react with B will generate product C and D in this case, and also draw the free energy as a function of reaction coordinate. In this case, if we try to end the catalyst Z, and what happened on the free energy versus the plot of free energy versus the reaction coordinate. By ending this catalyst, we can observe the energy barrier or activation energy will be decreased, so that will allow more reactants can overcome this energy barrier to generate more product. So that's the reason why the reaction rate can significantly increase. So the catalytic reaction for sure with a reduced energy barrier compared to the activation energy before ending catalyst. And regarding to these chemical equations, the driving force is also the delta G, okay? And you can confirm whether the delta G is smaller than 0 is negative. So that will tell you the reaction directions, right? Okay. So now, next I'm going to show you what factors can modulate the rate equation. As you know, the rate equation can be expressed like this. Included the rate constant means the energy barrier, working temperature, and also the concentration of reactants and corresponding stoichiometry coefficient or the reaction orders. So in homogeneous reactions, what factors can modulate the rate equation would be the temperature and also if the reactants are gas, so it will be a partial pressure. If they are the solid or liquid phase, it will be the composition of the reactants. And if the chemical reaction you deal with belongs to heterogeneous chemical reactions, you still additionally you need to consider the heat or mass transfer between or among different phases. For example, the reaction we talk about here is the burning of a coal. So the gas oxygen need to diffuse through this film layer or diffuse to arrive on the surface of this coal and can start the chemical reaction, which means the oxygen react with a carbon can generate carbon dioxide, right? And these reactions will consume the mass of this coal. So the size of the diameter of this coal will get smaller, so will be like this small. So this will be, and in the meantime, probably it will generate some heat, right? So the heat is going to diffuse out, right? But if the heat remain surrounding the heat stay here, it will increase the temperature of this reaction of this chemical equations. So under this situation, the heat transport rate will also affect this rate equation, right? If the heat can easily diffuse outside and the temperature probably will decrease back to room temperature, then the rate equation will be decreased in the meantime, right? But however, if the heat cannot successfully diffuse out, will remain surrounding this core, so the working temperature will be increased. So the rate equation, the reaction rate will increase in the meantime. So you need to consider the mass and the heat transfer among different phases. So that make heterogeneous chemical reactions more difficult or more complicated compared to that in the homogeneous chemical reactions. So now I'm going to give you questions. If we have solid A react with solid B and generate product C and gas D, these reactions occur in a sealed container or in an open space. Any difference in generation rate of product C? Any difference? And which one will be faster? Which one is faster? So as you know, in the sealed container, the concentration of the product will get higher and higher, right? So based on the Lee-Chatter's principle, when any system at equilibrium condition subject to change in concentration, temperature, or pressure, then the system will readjust itself, right? So when this increase, so it will slow down the reaction rate of these chemical reactions. So if it is open space, then the reaction will be faster, right? Because in the open phase, the concentration of a product will be lower than that in the sealed container. So that will help the reaction go to right-handed side, go all the way to the right-handed side, will speed up the reaction rate. And the other, for your reference, would be based on the rate equation shown here. Do we have chance to estimate the activation energy or energy barrier of my interesting chemical equation? And how to do that? Yes, you can do that, right? As long as you measure the consumption rate of reactants at different temperature and plot a log RA versus 1 over T, and after fitting, the slope will be correlated, associated with activation energy or energy barrier of these chemical equations. Okay, so let's move to, we want to talk more about the rate equations, but because different types of chemical equations and we are interested or we dealing with, so actually there are different units to a unit of rate equation shown here. So here the Ri actually is the consumption rate of if we assume I is a reactant, consumption rate of reactants per reaction volume. We call this Ri. Ri prime, we got a prime here, means the consumption rate of reactants per reactant mass. The difference just this is per reaction volume, this is per reactant mass. And this double prime is a consumption rate of reactants per interfacial reaction area. Okay, so based on this three rate equation, and the difference between them actually is just the unit here. So, but the consumption rate of reactants should remain constant when we talk about the same chemical reactions, right? So based on this, we know the relationship between Ri, Ri prime, and Ri double prime can be expressed like this. Vri equals to Wri prime equals to S Ri double prime. All this are equals to dNi over dt consumption rate of reactants. And also, I just want to put the rate equation shown here and just remind you the rate equation consumption rate of reactants can depend on the rate coefficient K, concentration of reactants, and also the reaction orders. Under some case, the reaction order will be identical with the stoichiometry coefficient shown in the chemical equation, but sometimes not. Okay, so we will talk this later in next slide. But next, in your textbook, he want to show you some scale about the reaction rate, means how slow, how fast your rate equation is. So they give you some examples, and the unit here will be the consumption rate of reactant A per cubic meter. So the slowest one is 10 to minus 4 will be sewage treatment. Means that you have a company which deal with the wastewater. You converted the wastewater to the general water, so it's we call the sewage treatment. And the human at rest is in between the 10 to minus 2 to 10 to minus 3. but the jet engine or rocket engine can up to the reaction rate is faster, very fast, is 10 to 3 to 10 to 4. So I'm going to give you an example and hope you can simply calculate the consumption rate of reactants. So the example here is we have a human being with 75 kilograms. He consumes 6,000 kcal food per day. And based on this, can you write down the rate equation or consumption rate of the oxygen in this for this human being? So based on this, we know that 6,000 kcal food per day actually generate the heat or energy for human being, right? And what kind or what type of energy generation way it will be or it happens in human being will be you take the food due to the glucose can react with oxygen and generate carbon dioxide and water, and this will generate heat by around 2816 kcal, right? So this reaction can generate heat. It will be exothermic reactions. And based on these equations, if we want to describe the rate equation or the reaction rate, you can either express by the consumption rate of glucose or consumption rate of oxygen. And here we use a consumption rate of oxygen as our indicator to describe how fast this chemical reaction is. So consumption rate of oxygen per univalent. So here, the consumption rate of oxygen will be how to get this one is because when you assume 1 mole of glucose, you will assume 6 mole of oxygen, right? And the delta H will be like this. So we use 6,000 kcal to divide it by this. We can know how many glucose we can take per day. The human being can take per day, and times 6 is the consumption rate of the oxygen in moles. The unit will be in moles per day, right? And now this you know, right? This will be the moles per day, and the volume because you know the weight. So we assume the density for the human being will be expressed like this. So you can easily get the consumption rate of the oxygen expressed like this. And the order is 10 to minus 3 moles per second per cubic meter. And don't forget the minus means the consumption rate. If you use a plus, will be the generation rate. Okay, so this the order actually is similar with we talking about in previous slide. Okay, so this is the we use the consumption rate of oxygen to express to show you the reaction rate for this chemical equation, right? But on the other hand, you also can use the consumption rate of the glucose to represent the reaction rate for these chemical equations. So my question would be, the consumption rate of oxygen equals to consumption rate of glucose times what? What's the relationship between the consumption of oxygen and consumption rate of the glucose? It's 1 over 2 or 1 over 6 or times 6. If you consume 1 glucose, you will consume 6 moles of oxygen, 6 moles of oxygen, 1 moles of glucose, so it should be times 6. So in order to show you how fast, what's the reaction rate for specific chemical equations, you can use the consumption of it, no matter is which reactants is okay, or even you can use a generation rate products can be is okay. But in here, I just want to highlight if we want to express the reaction rate for this equation in glucose and in oxygen, there's a ratio in between, okay? Okay, next I'm going to show you what's the difference between the elementary and non-elementary reactions. And what's the elementary reactions? It's quite important, especially because it will help you to formulate the rate equation easily in elementary reactions. Okay, so what's the elementary reactions? Which it means the chemical species react directly, highlight this directly to form the product in a single reaction step and also with a single transition state. So your reactants will react directly to form the product. So means A bond react with B will directly generate R in this single reaction step and also with single transition state. What's a transition state? Means you only have one energy barrier. So I grab some figures to demonstrate this one. This vertical is energy as a function of reaction coordinate. And this is reactants, this is products. And one transition state means like this, shown in the black curve. And what's the multiple transition state? Multiple transition state like the red curve. Okay, so if if it belongs to elementary reactions, for sure it is A directly react with B and generate R in this single reaction step. So when you try to write down the rate equation or consumption rate to describe these chemical equations, so you can either write down the consumption rate of Ra equals to consumption rate of Rb because when you consume, because 1A will be directly react with 1B and generate 1R. So you can also equals to RR. Minus means consumption rate and plus means the generation. And this because one more and generate one more. So here will be equal to, if the rate constant to the right hand side is K, so it will be KCACB. The reaction order is identical with the stoichiometry coefficient. In this case, we call it as a elementary reaction. So Ca, the reaction order 1, and Cp, the reaction order is 1. This we mean we say this type of chemical reaction is an elementary reaction. And next we try the other case, right? 1B react with 2D and generate 3T. So the difference between these two actually is the coefficient, stoichiometry coefficient, 1, 1, 1, right? But here is 1 react with 2D and generate 3T. So in this case, when you try to write down the consumption rate for Rb minus Rb, and also we assume the rate constant for the forward reaction will be Kb. So it will be Kb, Cb1 and Cd2 to 2. And consumption rate for Rd also will be use Kd, Cb1 and Cd2. And Rt actually is the KT Cb Cd squared. And interestingly, you observe the concentration part for these three are identical, are the same, right? The only difference actually is Kb, Kd, and Kt, and also Rb, Rd, and Rt will be different. Why? Because you assume 1b will assume 2D and generate 3T. So RB, RD, and RT will be different, and they have this type of relationship, right? You consume 1B, you will consume 2D, so you times 1 over 2, and generate 3T, so 1 divided by 3. So you have this relationship between RB, RD, and RT. And this will be identical, so you find the consumption rate or generation rate of will be proportional with the rate constant. So the rate constant KB, KD, and KT also have this relationship. Okay, so this is quite important. Actually, this concept we show you in here, the same idea. Okay, and what's the non-elementary reactions? Non-elementary reaction actually is not happens directly. I mean, the chemical reactants not react directly. Non-elementary reaction actually is composed of multiple elementary reactions, can be composed of 2 or more multiple elementary reactions. So its reaction rate is determined by the couple rate equation of elementary reactions. For example, like you have a nitrogen react with 3 hydrogen and generate 2 NH3. And this is a reversible reaction. So you have forward rate constant K1 and backward rate constant K2. When you check the rate equation, show to generation rate of NH3 show like this, and this is it's more complicated because it's K1 and times N2 and H3 this order and divided by this one, and also minus the K2 this one, and based on this rate equation, actually it's not as simple as this one, right? So for sure, this is not elementary reaction. This for sure is involve 2 or more elementary reactions and lead this kind of complicated rate equation. So this is a non-elementary reaction. But as long as you know the rate equation, what's the rate equation looks like? If it looks like the reaction order is identical with the stoichiometry coefficient shown in the chemical reaction, for sure this will be the elementary reaction. If not, it is non-elementary reaction. But if you have no idea about the rate equation, what the rate equation looks like, and are there any easy way to guess it which belongs to elementary and which belongs to non-elementary reactions? So I will give you some suggestion, like you can consider the probability part. 1A bond will react with 1B is easy to generate R, right? And 1B simultaneously react with 2D, the probability to be lower, right? Because you need to react with 2D simultaneously in the meantime. The probability to be lower, right? So for this case, I will guess it belongs to elementary reactions. But when the numbers of molecules increase to 1 nitrogen simultaneously react with 3 hydrogen, the probability for sure will be much lower. So in this case, I will guess it belongs to non-elementary reactions. Not really 1 nitrogen directly react with 3 hydrogen in the meantime. Okay, so in this case, I will guess it belongs to non-elementary reactions.